Okay, let's get this stream started. Good morning. Let's see how bad the lag is today. Okay. So, good morning, whoever is awake and listening. Welcome to another fun Kang Classroom episode. So today's topic is going to be a dual credit lecture. So those of you paying attention, or those of you on right now, we're halfway done with chapter 6. We're getting pretty close to being ready for the exam. I mean, assuming we can keep this pace and assuming this goes to the end of the school year, then I think April 22nd, whatever I have the date set to right now, is a pretty good idea. It's probably going to stick. So plan on having your homework done by then. I have 2 announcements before we get started. One, I'm going to try to pull up the Google Classroom while I'm talking, but I did edit a post on the Google Classroom, and I also posted on Twitter if you didn't get a chance to look. But, I mean, it doesn't matter which one. I posted it on both, but actually I have 3 announcements. One is this Friday is a holiday. It's Good Friday, right before Easter. So none of your teachers are required to host any office hours. I will not be on personally. I mean, I'll be available throughout the day. I'll probably answer emails as I get them, but my family is going to be doing churchy things online with our church friends. So I don't know how available I'll be on Friday. And all your teachers, they're all doing that. Okay. The other thing is if you are part of an extra credit group, those of you that logged on Friday and you actually want to participate, you're going to have handfuls of checkpoints that you need to meet in order to continue working on the project, and one of them is due tomorrow. So one of them, checkpoint number 1, not a whole lot of work to actually do, but I need you to fill out this Google form right here, and you see some people turned it in, but I need you to fill out this Google form, and all I need are your group members, who's in your group, and then the name of your island so far. This is mostly just so I get a feel for what, how many groups are participating, and make sure your names are all school appropriate, I guess. So that's it. So, oh, whoops. Oh, wait, yeah, leave. Okay, so if you are in the extra credit, be sure you are doing that. Other announcements. Hold on, I had one more announcement. I have no idea. It was related to the Google Classroom. Huh. Well, obviously wasn't that important. If I think of it, then we'll talk about it. Okay, so let's talk about vectors today. So the earlier parts of chapter 6, we were talking about triangles in general. Right triangles, and then just general triangles. How do you solve with law of sines and cosines? So now we're going to learn about vectors. And vectors are going to be related because some of the word problems you'll use law of sines and cosines, but a vector is just an arrow, if you remember this from your physics classes. It has a magnitude, it has a direction, and for us in this class, magnitude is just going to be how long the arrow is, and direction is just going to be what angle you're facing from 0 degrees. So scalars and vectors, the definition or the difference between a scalar and a vector, and I'm going to try my best not to just read all these slides to you because we have a lot of vocabulary to talk about today. But a scalar is just something with a magnitude and no direction, so it's how big something is, not where it's facing. If you put in the direction, you can now call it a vector, and all vectors have an initial and a terminal point, and then the different ways that you can denote them or different ways that you can write down how to refer to them are like this. So here's a vector. You've got point P, which begins the vector, you got point Q, which ends the vector, and notice how there is a direction to that. It has to go from P to Q. So if you want to write that out, you write out PQ. The first point is the beginning point, the second point is the ending point, and notice how the little arrow on top of it points towards Q to tell you that you're pointing at Q. We usually use bold lowercase letters if we're going to use a shortcut name for them, so you'll see vectors be called both of those things. And then if you ever see these 2 lines or 4 lines on the outside of a vector name, that's talking about the magnitude of the vector, or talking about the length of the vector. So the letter by itself is talking about the whole vector. The thing with the magnitude lines is telling you how long the vector is. So if we got out a ruler and we tried to measure how long that is, that would be the magnitude. More vocabulary. The 0 vector is a vector with a length or a magnitude of 0. It technically still has to have a direction, but who cares, because it's because it's 0 long. You can't see it anyways. 2 vectors are opposite if they are the exact same length, but the arrowhead just points in opposite directions. So parallel to each other. And they have to be parallel, because if they're facing opposite directions, they would be 180 degrees opposite of each other in terms of angles, or pi radians. Okay. So how do you add vectors together? And this kind of tells you what to do, but you're going to take 2 vectors that are v and w here. We'll just go ahead and draw a sketch. So you've got vector v, and you've got vector w, something like that. Now if you want to draw the result of adding them together, you're just going to take w, the second vector, you're going to slide it over to where the beginning of w lines up with the end of v. And this is something you're allowed to do with vectors. As long as you don't twist or stretch the vector, you're allowed to translate it wherever you want, is what we would say. So move vector w over to vector v. So we'll just do this. As long as you maintain the same magnitude and direction, it's fine. And now your resulting vector is from the beginning of v to the end of w. So it's kind of like you make a triangle. And then the note there at the bottom, addition is commutative. So if you had gone w first, then v, see how you still end up with the same blue arrow, you still end up with the same resultant. You're allowed to add vectors in whatever order you want. Okay. Okay. So scalars, remember a scalar is just a number. Sorry, my wife is apparently needing something, but she doesn't want to interrupt my lecture. Okay, so a scalar is just a number, something without a direction. So you can take a vector and multiply by a number. So we call it multiplying by a scalar. So all you do is if you multiply a vector by 2, you just make it twice as long. If you multiply it by 3, you make it 3 times as long. The key here is that you have the exact same direction. The only case where that's not true is if you have a negative number you're multiplying by. So if you multiply something by 2, you're going to make it twice as long. If you multiply something by negative 2, you're going to make it twice as long, and you're going to turn it around. You're going to flip it around. So it changes the direction of the arrowhead, I guess. And then, of course, if you multiply by 0, you end up getting the 0 vector. So here is an example similar to what you'll see on your homework. Graph 2u plus v minus w. So we're going to do what we did earlier. We're going to slide vectors over or rewrite them in different places, as long as we maintain the same magnitude and direction. So here's u, the first one down here. It goes up by a length of 3. So if I multiply it by 2, it should go up by a length of 6. So there's 2u. Now I want to add on v. So right now vector v goes, here's the vector v. It goes right by 2, up by 4. So we're going to do the same thing. Starting at the end of 2u, go right 2, up 4, and I'm a little up past the window. There's v. And now minus w. When you subtract of it, remember subtraction is the same thing as adding a negative. So I just need to take vector w, make it negative, and then add it on to the end of v. So what does negative w look like? It's the same thing except the arrowhead's here instead of here. So now negative w goes to the left by 4 and up by 2. So that's what we're going to do. So left by 4. So we're right there on the y-axis, up 2. So our resulting vector, our final one, starting from the very beginning of the problem up to the end of w. There we go. So there's 2u plus v minus w. Every time I do this example, I always think it looks like Phineas from Phineas and Ferb. I can't draw, but there you go. I should probably erase that. Alright, I'm just entertaining myself. Okay. Oh, I just saw chat. Good morning, Alyssa. It's nice to see people actually awake in the morning. It's funny, the first week we did this, we had like 30 people online every day on average, and now we're getting about 5, maybe, on a good day. I mean, that's why I'm recording them, but still, it's funny. Okay. Algebraic vectors. So another way, there's going to be a lot of different things we do with just the general definitions of a vector. As long as you remember as you do this entire assignment that a vector is just an arrow and it has a magnitude and direction. If you just remember that fact, most of it should be okay. What this whole slide is saying, and I know it's a little wordy, it's that you can, one of the properties of vectors, one of the things we did to make this problem possible was that you're allowed to take a vector and move it around anywhere you want, as long as you don't turn it and as long as you don't stretch it. So it can take any vector. If you take any single vector in the world, you can always slide it to where its initial point is 0, 0. So that means that if you from your initial to your starting point, if you go right 4 and up 3 or something like that, if you move the initial point back to 0, 0, that means the end point has to be 4, 3, because you have to go over 4, up 3. So we can define vectors basically all the time as the initial point being on 0, 0. So if you ever see this little symbol right here, the little, I actually don't know what they're called, but those things on the ends of a vector name, that means you're calling it this specific vector that starts at 0, 0. So some people call it a position vector. I don't know all the official terminology, but anyways, you can find the magnitude using the Pythagorean theorem, because if you have it at 0, 0, you can do Pythagorean theorem to find the length of the arrow that you drew. So if you have something that has an initial point and a terminal point somewhere in space, if you want to rewrite it as this position vector thing, this thing with the little initial point at 0, 0, you just have to slide it over and down, or wherever you happen to be right now. Slide it over to where the initial point is 0, 0, so you're subtracting away x1 from x2. Okay. So here's a vector, initial points at 4, -2, terminal point -1, 3. Write v as a position vector. It helps to draw a picture sometimes if you can't figure out why the numbers work the way they do. So if p is at 4, -2, and q is at -1, 3, And remember, it goes from P to Q because the initial point's P. So if you just use the sketch to get the answer, you see how you take this whole arrow, and currently it goes to the left by 5. It goes to the left by 5, and then it goes up 1, 2, 3, 4, 5. 5. That would be negative because you're going to the left. So if I redraw this, there we go. So negative 5, 5 for the ending point. So now if you see the math, we would do, and hopefully this works out towards the same, you do negative 1 minus 4 for the x-coordinate, and then 3 minus negative 2 for the y-coordinate, and we get the position vector to be negative 5, 5. So we draw the little symbols there to denote that we're actually starting the vector at 0, 0. So there's the picture way and the algebraic way of figuring it out. Okay, so let's do actual operations with vectors. So we're not drawing these anymore, we're actually finding them. So v is a position vector, w is a position vector. We can add them together, so v plus w. So again, you could draw the picture and figure it out if you want. You could slide w over to the end of v. Or since they're position vectors and they both have the same origin, they both have the same initial point, if you want the new x and y coordinates, you're just going to add the x's and y's together. So that makes this nice. So we just get 2 plus negative 4, comma 3 plus 1. So here this answer is negative 2, comma 4. If you just think about a quick sketch, if you draw them out, you could see it too. All right, b, negative 2v, so we're multiplying by a scalar. So we take v and just multiply both those numbers by negative 2. So it's kind of like we have negative 2 like on the outside of a parentheses. So we end up getting negative 4, comma negative 6. 2v minus w, so we got a little bit of both to do. So just like normal algebra, you want to distribute the 2 first before you subtract the w. So 2v is just multiplying by 2, not negative 2. So it's just 4, comma 6. We want to subtract away w. So we end up with 4 minus negative 4. And then we want to subtract away 6 minus 1. So we're subtracting away w. So we end up with 8, comma 5. And then finally for D, notice how it's the same vector as C. So now we just want the magnitude of 2v minus w. That's what that symbol means. I already know it's a position vector, so all I have to do is Pythagorean theorem with 5 and 8. So 5 squared plus 8 squared. So you get 25 plus 64. Square root of 89, which shouldn't reduce. Oh, wrote behind my face again. It's 89. There you go. 89. Whee! I'll do like the little DVD, little bouncing thing, like on The Office. Okay, I'm done playing. Okay, the unit vector. So sometimes you don't care about the magnitude of a vector, you only care about what direction it's facing. So you kind of want to standardize something to where it only has a magnitude of 1. So, for instance, if you have something with a magnitude of 11, you could just divide it by 11, right? Multiply by a scalar of 1/11th, and you end up changing it to a magnitude of 1. So if you take a vector and you want to take away the magnitude, if you want to create the magnitude of 1, you just have to divide by that magnitude. The direction stays the same because you don't change directions when you multiply by a number, and you just get a magnitude of 1. So find a unit vector in the direction of 3, -4. So it's a position vector. You have the little pointy parentheses things. So right now it's going over 3, down 4. So there's vector v. I want to find the same vector that only has a magnitude of 1. So I want the unit vector there. So notice how it's facing the exact same direction, but I need to divide by something. So I need to find the magnitude of v here. Luckily, we have a Pythagorean triple here, because this is a 3, 4, 5 triangle. So the magnitude is 5. So the unit vector u is going to be 1/5 times v. So it's going to be 3/5, comma, -4/5. And you can prove it to yourself if you do Pythagorean. I keep writing behind my face again. You can prove this with Pythagorean theorem. If you do Pythagorean theorem with 3/5 and 4/5, you get a hypotenuse of 1. Y'all hear my kids screaming outside? Okay, so now that we know what a unit vector is, we have two unit vectors that we use to standardize vectors all the time. It's one going in the x direction, one going in the y direction. So let me draw a quick picture of these. We save the letters I and j when we talk about vectors because those are going to be the names of particular, special vectors. So I is not imaginary like we're used to. This is a bold I, which you can't, if you can't tell. The one that just goes over by 1 this way we call I, and the one that just goes up like this in 1 we call j. So if you have a position vector, remember that phrase means that you're starting at 0, 0. You can actually break it up into multiples of the I vector plus multiples of the j vector. So if I tell you something is 4, 7, right? So I know a picture of this would look like that. But another way of writing this would be 4i plus 7j. Because you're just taking the I vector, the one that's pointing to the right, multiply it by 4. So there's 4i. You're taking 7j, which is right there, 7 times what's pointing up, and then adding them together. So remember, you're allowed to slide this 7j over, and then you do the hypotenuse. So it's just another way, again, of writing a vector. You're going to see it written both of these ways many times, so just get used to either or. Especially in classes past this one, those of you that take linear algebra, those of you that take, I don't know how much vector stuff you do in differential equations, but those are going to be most of y'all's next math classes after this one. It's going to be either linear algebra or differential equations, or you'll finally be starting calculus. Okay, so here is vectors written in ij form. So they give you a definition for u, definition for v, and let's find u minus 3v, and then let's find the magnitude. So u is left alone, minus 3v, so let's write that out. What is negative 3v? Remember, we're distributing a negative 3 here. So that's going to be negative 6i minus 15j. Go. So u plus negative 3v, or u minus 3v, is going to give us negative 2i minus 8j. So same vector, I want to find the magnitude. So we're going to do Pythagorean theorem with negative 2 and negative 8. There we go. So we end up with square root of 68. And that definitely looks for sure like it breaks up, right? So quick reminder. I mean, you could just do it by hand. You could try to divide by 4. It does work. You could try to divide by 9. This one's not going to work. By 16. Just try to divide by perfect squares. You know, divide by 25, divide by 36, so on and so forth. Or you can just do 68 divided by x and take a look at the table. Right? You want to look for perfect squares that work. And it ends up 4 and 17 end up being the only ones that work. But you could head all the way over to 17 and 4 to see that. But since this is 4 times 17, this is now 2 square root of 17. One more time. Move my face out of the way. There we go. All right. I don't see any questions in chat so far, so let's keep going. We're almost done. Okay, so if you have a position vector, remember you're allowed to write it as I and j. So you can actually use sines and cosines to figure out what the components of the position vector are. So if you only know the angle, so I'll write up here. If you know theta, you can actually break up. So for instance, let me draw a picture to help you. Let's say I'm doing a backwards problem. Let's say I know the magnitude and I know the angle. I can actually find the x and y components by using trigonometry, by using the stuff we just talked about in chapters 4 and 5. You can just do cosine to find the x coordinate and sine to find the y coordinate and just write it in vector notation by multiplying by I and j. If you want to go the other way and you want to know the direction of the vector, you can just use inverse tangent down here because you're going to inverse tangent both sides. You can use inverse tangent to figure out what the angle is if you know the components. So you can do this in both directions. So it should be, yeah. So last problem. Find the magnitude and the direction of angle theta of the vector v negative 4i plus 3j, round theta to the nearest hundredth of a degree. So I've got two parts of the problem. I've got to find the magnitude and I have to find theta. Well, the magnitude part's going to be kind of easy. Start to recognize these triples, right? So 3, 4, 5 right triangle, magnitude is 5. Yay, we're done with that part. Now the direction, so if you do a quick sketch, negative 4 up 3, I want to find that theta. Well, I know the x and y component. This is negative 4 and this is 3. I know the hypotenuse too. I know everything about this triangle. So you can find the angle however you want. We're going to use inverse tangent because that's what the slide told us to. Also, there's a chance we screwed up the 5, right, quote unquote. So we don't want to use it. So tangent of theta is just going to be opposite over adjacent. So 3 over, and now technically negative 4 here. We're just treating it like a triangle for now. Now we're going to inverse tangent both sides. So we'll head to our calculator. Inverse tangent of 3/4. Make sure we're in degree mode, hopefully. We are. So we've got 36.9 degrees. But that's not our answer. That's what the angle inside of the triangle would be. right there. That's what theta would be in there. But direction angles, if you remember from a while ago, are always from 0 degrees. So we want this angle. Answer. So we actually need to find the supplement of 36.9. We need to do 180 minus. So our theta, our answer is 180 minus 36.9. That gives us 143.1. So our direction is 143.1. And again, the reason we had to do that, and one more time, always writing behind my face. There we are. The whole reason that we had to do that is because direction angles are always defined from 0 degrees, not that little one in the triangle we care about, or that we calculated. So we used inverse tangent to find the angle inside the triangle, but then we did the whole 180 minus. Remember I mentioned a little bit earlier why we ignore the negative on the 4? If you had just typed in inverse tangent of 3 divided by negative 4, remember inverse tangent can only give you negative angles. So the negative 36.9, that still doesn't make any sense in terms of how you get 143.1. We just got the 36.9 as a geometry problem, and then we had to interpret it ourselves to figure out what quadrant we were in, what the reference was, what we needed. So that is the whole reason. Okay, so that's our 6-4 lecture for today. All right, I don't see any questions. Does anyone have any questions in chat? I see there's a handful of you that actually have a name logged on. Hopefully school and everything is going well for y'all. I know people are still in an adjustment period. I still have a solid 10 students that haven't gotten back to me yet, so hopefully they're all right. I mean, I've emailed and phone called, so we'll see what I can only do so much. Stay safe out there in Baytown. I read a article that y'all had like 7 confirmed cases as of a couple of days ago. So wash your hands and stay 6 feet away from people. And I will see y'all next time.